At the base of our description of statistical physics is the Hamiltonian of a system. The Hamiltonian is defined in a six-dimensional phase space in which the Hamiltonian depends on the translational part, which only depends on the momentum of each particle, and a potential part, which depends on the position. Now, in the case of an ideal gas, meaning there is no interaction between the particles, this Hamiltonian is just given as a sum on the translational part of each particle and a sum on the potential of each particle. In such a case, we found that the partition function of the system is simply given by product of the partition functions of every particle, and the thermodynamic potential is given by the sum of the potentials of every particle, which for identical particle just n times the thermodynamic potential of a single particle. For a real gas, however, this does not hold. For a real gas, the potential is dependent on the position of more than one particles, typically is dependent on the distance of two particles. Hence, the partition function will not be product of partition function of the individual particles anymore. Now, one way to elevate this problem is the so-called mean field approximation. In the mean field approximation, we will assume that we can describe the interactions between particles by a mean interaction, such that the interaction potential now again leads to a sum of the interaction potentials of individual particles, and we can use the description of the ideal gas to describe also interacting gases. This method we will develop in this clip. As an example, we will use the nematic gas in 2D. Nematic particles are particles that have one preferred direction. We will describe nematic particles as solid rod of length L and width which is much smaller than L, let's say it's 0, and they have a mass m. Those particles are now positioned randomly on a surface of area A, and we apply the rule that those particles may not overlap. Particles may only align along the x or the y direction. Now, at low density, we will have a random orientation, meaning that the number of x particles is equal to that of y particles. Yet by increasing the number of particles at high density, we would need to arrange all particles in an ordered fashion in order to accommodate any additional particles. The question we would like to ask in this clip is, how can we describe this transition from a random orientation to an ordered and aligned orientation at high density, which characterizes the nematic phase transition? Now, our very artificial system is not that far from an application. Actually, in the LCD screen that you have in front of you, nematic molecules are used in order to display the different colors and also the different gray levels on your screen. Hence, what we describe has a significant technological impact. Our description starts from the canonical ensemble, in which Z is given by the number of particles in X and X, number of particles and Y, beta, and the area. Further, we use the classical description, hence Z is given by 1 divided by n x factorial and y factorial h to the power 2n times the phase space integral on P and Q e to the minus beta h of P and Q. After integration on the momentum space, we finally obtain that Z is given by 1 divided by nx factorial and y factorial times 1 divided by lambda thermal to the power 2n integral on dqx and dqy e to the minus beta u, the interaction potential between all those particles, depending on space variable qx and qy. Now we introduce a non-overlap function, f, which depends on all the positions of particles x and y, is equal to e to the minus beta u of qx and qy, which is 0 if there is overlap and 1 if there is no overlap. We can rewrite the partition function in terms of the non-overlap. Now, in order to proceed, we have to realize that the x system is in equilibrium to the y system. In this particular example, this means that the affinity of x has to be the affinity of y. Let's calculate the affinity of x. Well, from the definition, we know that the affinity of x is given by del of the log of the partition function with respect to del nx. Knowing that this derivative is discrete in the number of particles, we rewrite the equation leading to that alpha of x is given by the log of the partition function of particle nx plus 1 with respect to the partition function of nx. Let's look into this ratio, which we will call z of plus 1 divided by z. Now, from the prefactors, only that of the nx plus 1 particle stays. Now, z we already defined using the overlap function. And for z of plus 1, we still have the same integral, yet we have to extend it with the dimension of the nx plus 1 particle, which we call capital Q, and the respective overlap function f of capital Q, which is depending on all the positions of all y particles. The term that we just added, the integral on d2q f of q qy, is nothing else like the allowed area of particle nx plus 1. Let's call it a, which only depends on qy. Now, filling in our definition into the prior equation, we see that the ratio that we just obtained is nothing else like the mean allowed area for this additional particle. We now assume that all y particles are randomly placed into the area A. Hence, the mean probability that placing a particle x at any position within the area A, given that there is already one y particle around, is P1 is equal to 1 minus L squared divided by A. As all y particles are randomly distributed, the probability for non-overlap of one x particle, given that there are ny y particles in this area, hence is 1 minus L squared divided by A to the power ny. This is the mean field approximation in that particular system. Now, taking this approximation, we can express the ratio of the mean allowed area of any x particle with respect to the area A is given by P and y, which for ny going to infinity is e to the minus L squared divided by small ny, where small ny is the density of y particles. So what we just derived is the ratio between z plus 1 and z, given by e to the minus L squared density of y particles divided by density of x particles, lambda thermal to the power 2. So if we summarize so far, we have derived an expression for alpha x as a log of the ratio of z plus 1 and z. Now, as of symmetry, a similar expression we would obtain for any ny particle, where the density in x and the density in y is interchanged, vice versa. Now let's come back to our initial question, whether there is a preferred orientation in the system. In order to quantify this, it is handy to define an order parameter. The order parameter gamma is equal to the ratio of nx minus ny divided by the total density of particles in the system. If gamma is plus 1, meaning that all particles are oriented in x direction, if gamma is equal to minus 1, all particles are aligned in y direction, and if gamma is equal to 0, we have a random orientation. Now, using the definition of gamma in the above equation, we come to an equation in terms of gamma, reading ln of 1 plus gamma minus ln of 1 minus gamma is equal to L squared and gamma. Using the inverse tanh definition, this can be further simplified, reading gamma is equal to tanh hyperbolic L squared times n divided by 2 times gamma. This equation is called the consistency equation. A consistency equation will always appear when applying mean field theory. In mean field theories, we assume that one particular observable, in this case the mean free area, is fixed for all particles in order to derive the partition function, yet the partition function is used to calculate back the observable by means of the respective partial derivative, and this has to be made consistent. That is the expression of the consistency equation. It is easiest to look on the consistency equation in graphical terms. Here I show the value of tanh A times gamma as a function of gamma. We see, depending on the value of A, the steepness of the curve increases. Now the requirement of the consistency equation is that the value of tanh A times gamma has to be equal to gamma. Hence, has to cross the diagonal of this graph shown as a black line. We see that there's always a crossing at gamma equals to 0. Gamma equal to 0 means that the number of x particles is equal to the number of y particles. That's the trivial solution of the problem. Yet for L squared n half larger than 1, we see that there are two additional solutions, meaning that the system will allow for asymmetry depending on the density of the particle. We can also plot the positions of the solutions to the consistency equation as a function of n, the density of particles. We see for very low density, gamma is 0, or the number of x particles is equal to the number of y particles. Yet increasing the density to L squared times n half larger than 1, meaning for a larger than half filling, we see the two other branches coming up. Either particles align into the x direction or particles align in the y direction. In that range, we also can plot the thermodynamic potential as a function of the density. What we find is that the thermodynamic potential at this density actually has two maxima, one at the x branch, one at the y branch, whereas the trivial solution for gamma equals to 0 is a minimum. Hence, this is an unstable situation. The process we just described is called spontaneous symmetry breaking. We start from an unordered system, a randomly ordered system. By increasing one of an external parameter, in this case the density, the system decides either to fall into the x branch or into the y branch. Spontaneous symmetry breaking is associated to phase transition, and for the example that we show here, to the so-called nematic phase transition. By increasing the density, either only the x particles or only the y particle will survive. Those kind of symmetry breaking events are ubiquitous processes that you find all over physics. One particular example is the Higgs boson that is described by a similar spontaneous symmetry breaking in the wave function, generating the mass of a particle.